All right, in this last video, we're just going to review a couple rules of probability and then do some examples to really drive in and I don't know the phrase I'm talking about, but to help, I guess. So in general, the probability of some event A, we just count out how many ways can we get this event to happen and divide by the total number of outcomes. And any probability has to be between 0% and 100%. We have also something called a complement, and you can calculate that by just subtracting the other thing from 1, right? 40% chance of this means 60% chance of not this. Okay? Or has to do with addition or addition. I'm going to make that happen, as painful as it is. And if they're disjoint, then it's a simple formula. But if they're not disjoint, then we have to add, we have to subtract actually, a third term. But if they're disjoint, then this last thing is just equal to 0. So you can always use this second formula. If you want to never use this first one, you can cross it out. You can always use this one. Similarly, for and is multiplication. That's the worst one. Multiplication. Multiplication, I don't know, is if we want two things to happen, usually one and then the other. So you can look at it as, oh no, the number of outcomes in both A and B divided by the total number of outcomes. Or you can also use this formula if they're independent. Okay, and if they're not independent, you can use that formula. Whoa. Again, disjoint means they can't happen at the same time. They're mutually exclusive. Independent means they're not dependent. Let's do some examples. All right, forget about this. It has nothing to do with participation. Let's just do this right here and see where we're at. So we have a random survey of automobiles parked in student and staff lots in a large university, classified by, we classified the brands of origin for these cars as seen in the table. So the American, European, or Asian makes of these cars compared to who's driving them. Another contingency table. This time our contingency table doesn't have totals. If you want, you can kind of pencil them in or pen them in, as it were. It would be helpful. Okay, so we add these up together. This is going to be 212. This is going to be 45. This is going to be 102. Adding up all of these, this is going to be 140, 195, and 117, 164. And hopefully this row and this column add up to the same thing. Okay, my Adobe is actually behaving a little bizarrely right now, but it doesn't really matter. We add up all of these right here, right there. You're going to get 257, 359. If you add up the other ones, you're also going to get 359. Great. So if you want, you can add this totals. These totals are usually going to make things easier, but you don't need them. Well, yeah, you kind of do. You at least need the grand total. You'll save you some work to do it, front load that work. So what's the probability a car is driven by a student and is American made? Okay, this is a joint probability. So driven by a student and is American made. Well, driven by students is everything in here. So what in this column is also American made? It's 107 out of the 359 total. Probability, just count how many are in both. Okay, and you could reduce this, write it as a percentage. And I already forgot what these numbers were. 107 divided by 359. That's going to be about 29.81%. But that's not the only way of getting this answer, right? We also know, well, it's the best way of getting this answer because they're not independent, right? These are not independent. So we don't want to really use that other formula because it's just going to have us kind of go backwards. All right. What's the probability a car is Asian made or is driven by a staff member? Okay. So are these mutually exclusive? Because if they're mutually exclusive, let's call this A and this B. If they're mutually exclusive, then the probability of A or B is the probability of A plus the probability of B. But if they're not mutually exclusive, we have to subtract the probability of A and B. And again, you can use the word and if you want instead of this intersection sign, this arch. So maybe you're not so good on whether something's mutually exclusive or not, but remember, we can just use this formula regardless. The first formula can only be used if they're mutually exclusive, but this full formula can be used all the time. So let's just use this one. What's the probability that it's Asian made? Well, 102 cars are Asian made out of 359. Okay, 102 out of 359 plus the probability that it's driven by a staff member. That's 164 divided by 359. Okay. 164 divided by 359. Now subtract that. What's the probability that it's Asian made and driven by a staff member? There's 47 out of 359 for that. So they weren't mutually exclusive. Another way of looking at this was here's all the Asian maids. Here's all the staff cars. Add up these four numbers like so, and you should get to the same answer. All right, let's type this into a calculator. Get our answer as a percent. 102 out of 359 plus 164 divided by 359 minus 47 divided by 359. That comes out to about 61.00%. We include the zeros here to show more precision. This shows that they're definitely zeros, but if we just wrote 61%, first off, it looks like I'm writing the letters GI. And second off, the real problem is then it could be 61.2, could be 61.3. We don't know. That's why those precision, those zeros are helpful. What's the probability that it's driven by what is the probability that a car that is driven by a student is American made? This is our assumption. This is our condition. This is conditional probability right now. Okay. So we're assuming that we're only looking at cars driven by students. What's the probability that if we only asked students that it's American made? We're only looking here. What's the probability in this subset that it's American made? 107 out of 195. As a percent, that's going to be 54.87. All right. What is the probability that a car is not European made? It's going to be 1 minus the probability that it is European made. Okay, what's the probability it's European made? 45 out of 359. Okay, so 1 minus 45 out of 359. Type that into a calculator, and you're going to get 87.47. Again, be very careful rounding when you have a 5 at the end. It rounds up if there's a 5, so it does round to 47. What's the probability that the car is Asian made given that it's driven by a staff member? So again, this is our assumption, our condition. So we're only looking at cars driven by staff members. We're only looking here. What's the probability out of those cars that it's Asian made? That's going to be 47 out of 164. Again, type that into a calculator. See what we get. 2866. Is origin independent of type of driver? No. I believe we've already shown that in some of these. We can show it more more precisely by just looking at the last example. Let's say this is an event A and this is event B. It's independent, right? If the probability of A given B equals the probability of A in general. But the probability of A given B we found in the last one, right? That's 28.66%. But the probability of just A, the probability that it's just Asian made, right? If we just look at, okay, what is just the probability that something is Asian made? 102 over 359. 102 over 359. That's 2841. That's actually very close. Interestingly enough, that the staff and student have a similar proportion of these ones. But notice that you don't have a similar proportion for the other ones. The other ones would have actually shown this a lot more, but either way, these are not the same. So these are actually close, like they're almost independent in a sense, but the other ones would be much more different, okay? If you checked other conditions as well, you'd really see that this is a very hard no, even though in this case, it's actually surprisingly close. Let's do some more examples. Imagine that you have a bag of 3 black chips, 4 red chips, 2 white chips, and 1 green chip. And it really says something about you, whether you're envisioning a bag of like tortilla chips or a bag of like gambling chips. which one are you? I thought tortilla chips. So, what's the probability of drawing a black chip? Probability of, I'm also pretty hungry right now, of drawing a black chip is just the number of black chips divided by the total. Should be 10 total, or 30%. White or green chip. Are these disjoint? Are these mutually exclusive? Yes. So in this case, that's going to be the probability of a white chip plus the probability of a green chip. Okay, that's 2 out of 10 plus 1 out of 10, or 30%. If they weren't disjoint, we'd also have to subtract by the probability of both. But there's no chance that something is white and green as a chip. What's the probability of drawing 3 red chips if they're replaced each time? That means these are independent. If they weren't replaced, then each draw would be different. But because they are replaced, each draw is the same. The probability of red and then red and then red again is just the probability of each event multiplied by itself. Or the probability of red cubed, which is 4 out of 10. Or 2/5. Multiply that all out. You're going to get 8 over 125, I think is what it simplifies to. Right? 2/5 cubed. 8 over 125. I don't know what that is. But I would guess it's about 6.4% exactly. That works better when I don't show you me using the calculator. What's the probability of drawing 3 red chips if the chips are removed each time? These are not independent anymore. Well, now, so the first one is still normal. The first one is still a 4 out of 10 chance. But for the second chip, there's not 10 chips anymore. There's only 9 chips remaining. And we've taken out a red chip already, right? In the first one, right here, we are removing a red chip. So now there's only 3 red chips remaining and 9 chips total. And for the next chip, there's only 2 red ones left out of 8 total. So if we multiply these all out, we're going to get 24 out of 720, I believe. I'm going to get myself into trouble doing math in my head like this. Let me know if you see anything wacky. 24 divided by 720 is 0.03 repeating. It's 1/30th. Or about 3.33%. All right, so this last example problem is, I don't want to spoil it for you. Let's look at it first. 56% of all American workers have a workplace retirement plan. 68% have health insurance, and 49% have both. We select an American worker at random, and we want to know some information. So this is information that is made a lot easier with the use of a contingency table. So let's make one. Okay, so retirement plan, yes and no. Health insurance, yes and no. Let's kind of go off to the side. Retirement, yes, and no. And health insurance, October, you better not be scratching on that bed. Going to be over here is yes and no. This is going to be our little contingency table. And again, hopefully the totals all add up to 100%. So 56% of all American workers have a workplace retirement plan. Okay, so 56% have retirement. So we go under retirement, the total for yes retirement, the total for yes for retirement is 56%, which likewise means that 44% do not have a retirement plan. Okay, and similarly, 68% have health insurance. So 68% have health insurance of yes, which means that 32% have a health insurance of no. Add up everything, you should get 100%. We're also told that 49% have both benefits. 49% is right here. Now this is kind of like one of those puzzles that I used to do as a kid, where it's kind of like getting to the end of Sudoku, I guess, too, kind of, in a little bit. If this is 49 and this is 56, you know, what does the other slot has to be? They have to add up to each other. So this has to be, whoa, that's the wrong button. This has to be 7%. And then if this is 49 and that's 68, it's going to have to be 19%. You don't have to use a contingency table for a problem like this, but it makes things a lot easier. And double check that this adds up both vertically and horizontally, that last box that we filled in. Okay, you don't need a contingency table here, but it makes the problem a lot easier to look at. So if you want to make one, go ahead and make one. Otherwise, you don't have to. So if you look at this, what's the probability that there's a retirement plan and health insurance? That's a probability of both. That's the 49% that we were given, right? Right here, yes and yes. Again, this is information that's given. We don't necessarily need the table for that. A little overkill, but it can be an assistance. What's the probability that they have a retirement plan or health insurance? So there's two ways. You could look at the contingency table, or you can do it without it. Probability of retirement plan or health insurance. These aren't mutually exclusive, so it's going to be the probability of a retirement plan plus the probability of health insurance minus the probability of both. So that's going to be the probability of a retirement plan, which is 56%, plus the probability of health insurance, which is 68%. And we have to get rid of double counting because 49% have both. And if you type this into a calculator, you should get 75%. Let's check our contingency table and see if that makes sense. Retirement or healthcare. Well, healthcare is this one. Retirement is this one. If we add up all of those three numbers on the inside, we get 56 plus 19 is 75. So again, just one way you can do it with or without the contingency table. It's all wholly optional making that table up there. What's the probability if they have health insurance? What's the probability they have health insurance if they have a retirement plan? This is our assumption. Okay, we can call that B. Health insurance is going to be A. So we're looking for the probability of health insurance given that they have a retirement plan. So our formula says this is going to be the probability of A and B, the probability of both, divided by the probability of just B. That is our formula for conditional probability that you can find up there. Well, the probability of both was 49%, divided by the probability of a retirement plan, which was 56%. Type this into a calculator and you should get your answer. 49 over 56 is going to give you 87.5%. And likewise, if we wanted to use our contingency table over here, what we could do is look at the probability given, like we're assuming that they have a retirement plan, so we're only looking here. What's the probability that they have health insurance? 49% out of 56%. So another way of you seeing how you can come up with that answer. Okay, so again, this up here is optional. It's a little extra work, but it can sometimes make things a little easier to calculate. And it shows the relationship between using a contingency table to get these probabilities directly or using these properties of probability that we've introduced in this module, in this unit. So good luck. Let me know if you have any questions. And I did it again. I knew there were 6. I looked and I knew there were 6. Given that they have health insurance, what's the probability that they also have a retirement plan? Okay, so again, now our assumption is up here. We can call that B. Probably they also have a retirement plan. That's A. Probability of A given B is the probability of both divided by the probability of the second. We could have used the same letters as before. It'd probably be helpful if we didn't rename A and B every single letter, but here we are. And again, the probability of both was 49%. Divided by the probability of health insurance, which was 68%. And that's going to come out to 49 over 68, which is about 72.06. Are having health insurance and a retirement plan independent events? Well, I'm going to say no. I'm doing the worst thing possible, giving my answer before finding out whether it's correct. Let's look. It's independent if the probability A given B is the same as the probability of A. Well, in the above example, we found that the probability of A given B was 72.06%. Whereas what's the probability of just getting a retirement plan? What's that just P of A? Retirement plan is 56%. Right, these are not the same. Not equal. Right? If you have health insurance, you're much more likely to also have a retirement plan. And there's a lot of factors that can go into that, but this video is already pretty long, so I won't do it. Are having these two benefits disjoint? And the answer is also no. They're not mutually exclusive. Right? Because it's possible to have both. In fact, about half have both. All right, and that kind of combines all these topics. Let me know if you have any questions, and good luck.